Hello. So, welcome to the new episode of the solid state physics course. And today I am going to expand on the idea that I discussed last time. So, what we discussed last time, so let us do a very small recap of what we is discussed last time. So, what we discussed was like pretty simple. It was Miller indices. So, mainly we talked about Miller indices and how through the concept of Miller indices we can actually connect the ideas of Lois condition and the Bragg's law. So these are the two things that we compared, and the bridge was Miller indices. Miller indices was something that we use to characterize or to label the Bragg plane, or the plane where the plane that we draw during the Bragg's law confirmation. Okay. So that are the Miller indices, and now we are going to expand on the ideas about how does the diffraction look. So what data do you get from diffraction, and from that data what more data or what more information about the um, the material you can extract. So during diffraction, I am going to talk more or less about a cubic crystal because that is the easiest case. Other cases are also there in nature, but it's like little bit difficult to actually see the diffraction data of a, let's say, hexagonal or triclinic or tetragonal crystal, and make sense of it. So it's a little tad bit harder. So I'm not going to go into that direction because that is not the point of the course. The point of the course is to give you a loose connection between the experimental diffraction and the theoretical structures that we are going to discuss. So, for example, we have a diffraction pattern. So, this is a cubic crystal. We know that it's a cubic crystal. So I will tell you that there will be some differences between cubic crystals and other crystals, how the diffraction things will look like. So as we will see, and as we saw actually, that the lattice spacing is actually given as h square plus k square plus l square divided by a square, where a is the lattice constant for the cubic lattice. So that is something we already derived in the last class. But in this class, what we are going to do is we are going to see that, okay, h, k, l are integers, right? So during the diffraction, when you take the diffraction data, you will basically get something like, um, for example, a peak here at certain angle. The peaks are not as broad as I'm drawing, but yeah, just bad drawing. So you will get peaks which are kind of separated, like the separation between two peaks will be pretty much the same for a cubic crystal. And why? So that has to do with this thing. So this is a theta, this is the theta, and this is the intensity. So this is a theta versus I plot, or sorry, I versus theta plot. And from Bragg's law, what we know that 2d 2 sorry 2d sine theta, so dhkl, these are the Bragg planes. 2d sine theta equals to n lambda. So that is what we know. We will mostly take n equals to 1 because actually the multiples of n can be actually absorbed into the d. So you can have, let's say, h equals to 1, k equals to 1, l equals to 1. You can also have h equals to 2, k equals to 2, l equals to 2. So all of this n, the multiplicity of n can actually be absorbed into the dhkl thing. So, for example, um, D111 is there. There can also be D222, which will be D111 by 2. So, this is actually corresponding to, let's say, D2D111 sine theta equals to 2 lambda. That will become 2D222 D222 sine theta equals to lambda. So the n is absorbed into the d11, so we are going to get rid of n. So from that, what we know is dhkl equals to lambda by 2 sine theta. So this is an important relation that we will be using to actually see that what the case is. And also, if you see, 1 by dhkl square will be 4 into sine square theta by lambda square, which is also going to be equal to 1 by a square, h square plus k square plus l square. So you can see that there is a periodic kind of pattern that is there, because HKL can be starting from 100, for which h square plus k square plus l square is 1. It can be 110, for it will be 2. It can be 111, it can be 3, it can be 200, 4, 210, 5, 211, 6. So yeah, like that, 2208, 3009. So you can see that the h square plus k square plus l square, which is directly proportional to sine square theta, it is taking kind of integral values, all of the integral 1, 2, 3, 4, 5, 6. Then there is a gap at 7. 7 is not present. Then 8, 9, 10. I think there is a gap at 11. So there are some gaps, but mostly the h square plus k square plus l square thing is taking all of the integral values. It can take all of the integral values 1, 2, 3, 4, 5, 6. So that's why you will see that these are kind of very periodic, as in this distance, this distance, this distance, this distance, they will be pretty much the same because of this 1, 2, 3, 4, every integral value being allowed. This is the result of this thing. But if you see hexagonal crystal, if you see tetragonal crystal, if you see triclinic crystal which has, these crystals have less symmetry. So due to these having less symmetry, what you will see is that these peaks will not be very uniformly spaced. They will be bunching of some peaks in some narrow region, because in those cases you will see that this 1, 2, 3, 4, 5, 6 pattern will be not there. There will be 1, 4, 5, maybe then 8, 9, 10. So in middle, the integers are not possible. The combinations of integers are not possible to get from h, k and l. Here the h square plus k square plus l square is a very simple function, and that's why you are getting like all sorts of integers. Okay, so that is one part, but that is not the main focus of our lecture today, because what we are going to see, it was a preliminary idea of how to read the tables, because some experimentalist will take some crystallographic data and then they need to read it. So what happens is, nowadays there are softwares which can read them for you, and actually what you can do is, after reading, you can actually assign them. This is 100, this is 110, this is 111, this is 200, this is 210. So like that you can actually assign Miller indices to the peaks. You can actually identify that which peak is coming from which Bragg plane diffraction. So that is something that but okay, for an unknown material you don't know whether it's cubic or not. So for those cases, all of the things are taken care of by some softwares nowadays. They can actually see, look at the peaks, and then they can assign values to those peaks automatically, because like it can, by trial and error, it can actually find out what kind of crystal it is, whether it's cubic, whether it's trigonal, whether it's triclinic, whatever it is. Then it can apply the respective math to get the peaks, the peak indexes. So now what we are going to talk about is, this thing was for a crystal. This thing was for a crystal, right? Where we had some planes, and we had, um, for example, we this was considering that there are no other atoms in between. So another good way of putting it is that this there are more ways to look at these kind of refraction. So for example, there is a more mathematical way. For example, what we are seeing here is, let's say there is a crystal. So I'm, for example, drawing a 2D crystal, and here what we can see is that there can be some atoms, right? And the diffraction can happen actually from all of the atoms simultaneously. So what we can see is there is another way of looking at things. So I will after I have discussed this, I will actually correspond this to the previous picture of the Miller indices where we saw a lot of peaks in Miller indices. Okay, so um, for example, here is a light source. Here is a light source. So let me draw it by yellow. Let's say here is a light source. So light falls. Let me draw a straight line. Yeah, the light falls on this atom. So for now, yeah, well, light also falls on this atom. Light also falls on this atom. Okay. Now there is a detector, which is shown by, let's say, pink. And what will happen is the light will, after going there, the light comes there. Okay. So now we want to see that what will be the phase, what will be the phase of the light, what will be the light, or what will it constructively interfere, will it destructively interfere. So for example, now let us actually consider, for simplicity, let us only consider two atoms. So we will go to more atoms, we will generalize it later. So let's say this is R before 1. So this is atom number 1, this is atom number 2. This is R before 2. This is R after 1. This is R after 2. So R before 1 is the light ray before reflecting the first atom. Okay. So, and R2 is the second atom, and RB2, R before 2, is the light ray before reflecting on the second atom. So what we will do is we will see what is the total phase. So this, let's say this is K, this is K, this is K also, approximately they are kind of equal, and but these are K prime and K prime. Okay, so we are looking at like Bragg stuff. We are looking at parallel light rays. Just like Bragg's law, we will assume that the K and this K are equal because this light ray is assumed to be very, very far away from the atoms. But this distance will be very, very small compared to the distance, this distance from the source to the point. So the phase of one, what it will be? I into e to the power k dot rb1 into, this will be the phase it will, the light ray will get before the reflection, then I k prime rb, sorry, ra1. This will be the phase of 1. And what will be the phase of 2? E to the power I k ra1 into e to the power I k prime, oh sorry, there is a mistake, rb2 e k prime ra2. So this will be the phase. Now we want to see what is the phase difference. If the phase difference is a multiple of 2 pi, then constructive. If it is an odd multiple of pi, then it's destructive. So if we actually see what is the phase, it will be e to the power I k dot rb1 plus k prime dot r a1 plus e to the power I k dot rb2 plus k prime dot r a2. Okay, so now if we, so it will be a little bit of math, but if we actually see that rb2, or maybe yeah, rb2 minus ra1 rb1 equals to r, if we take that, then you will see that r a1 minus r a2 will also be r. Okay, so from just from vector stuff, this is like r or maybe let me write it in different ink. So the red one is R. Let me write it more clearly. Yeah, so this is R. Okay, RB2 minus RB1 is R. Similarly, if you see, then RA1 minus RA2 will be also R. So if we put these things in these equations, what we will get is, we will get that this phase will actually reduce to some e to the power some I theta, some phase outside, into 1 plus e to the power I k prime minus k into R. So this is a profound result. So this is a very profound result. And k prime minus k is what? It is G from lowest condition. So I theta 1 plus e to the power I G dot R. So that is the way. Another way, same thing if we write, for example, with respect to this origin, let's say this is the origin. Okay, this is R1, the like respective positions of R1 and R2 are given. So we also know R1 minus R2 is R. So we can also write it to be e to the power I theta into e to the power Ig dot R1 plus e to the power Ig dot R2. That can also be written. So this can also be written in this form. So this is kind of the thing we need. So now we will see that what happens with different kind of crystals, because I think we discussed about FCC, BCC, simple cubic lattices, and from that we will see now that what happens. So like this will be the total phase of the light, which now what basically we are doing is we are considering an unit cell. But not only the unit cell, we are considering that in this unit cell there are multiple scattering centers, and we are seeing that when, at what angles these scattering centers will actually give you a constructive interference. So this is another way of looking at the same thing. So we are looking at the thing from different angles. So for simple cubic, so what is the basis? One basis atom, one a basis per unit cell at 0 comma 0 comma 0. So now the thing is, generally what we will do is, for example, there are n atoms in the unit cell, then the phase will be given as e to the power I theta summation of e to the power g dot r n, right? So that is conventional wisdom from what we got here. For two atoms, if this is the case, for multiple atoms, this will be the case. But in general, there will be a coefficient before each atom. So the coefficient depends on the structure of the atom. So for cesium, you will have a different F. For chlorine, you will have a different F. You will, for let's say potassium, you will have a different F for each element. Also depending on what theta you are giving the light to, what is the angle of reflection, the Fn will differ. But for a single theta, let's say that the theta is given, we are only looking at the experiment which has already been done at a given theta. So the Fn will basically, it will mainly represent the atoms. Different atoms will have different Fns. So that is something we need to consider. But we will only consider, now we will only consider homogeneous unit cells which have same atoms everywhere. So the Fn can be taken outside of the summation, because Fn will be the same for every n. So let's say we take it outside, and what is F we will discuss, and where does F come from we will discuss that. So yeah, so Fn is also called form factor of the atom. So Fn is called the form factor of the atom. So it's kind of like a scattering power of the atom. Okay, So for example, now we again come back to our example of simple cubic one basis. So this thing, the phase, let's say we call it P, it is already given by e to the power g dot 0. That's it. So there is no scattering actually. So there is, so it's 1. So it's always non-zero. So all of the peaks are possible, irrespective of the angle of the light ray. You can see, irrespective of the angle of the light ray, and irrespective of HKL, we will get something. So this G is given as a HKL, right? So yeah. So another way to look at it is, so G. So for mathematical consistency equals to H. So the HKL and the relation between G is given as this, right? That we already saw in the earlier class. So R, if it is given in fractional coordinates, let's say xa plus yb plus zc, right? Right, a, b, c are the lattice vectors, and x, y, z are the fractional coordinates. For a cubic crystal, G dot R will be given as hx plus ky plus zc plus lz, right? So then what the formula will become is, the P is equal to 1 plus, sorry, summation of n e to the power I h x n plus k y n plus l z n, where n sums over all of the atoms in the unit cell, and x n, y n, z n are the respective fractional coordinates. So this is the easier way, the mathematical way. For simple cubic, we will see it P to be 1. For, we are completely ignoring the phase factor, because this phase factor will cancel out during calculating the intensity, which is just given as P square, right? So when we will take the mod, the phase factor will just go away. For BCC, what we have is one atom at here, 0 comma 0 comma 0. So okay, let's go to the next page. For BCC, two atoms are there, 0 comma 0 comma 0, half comma half comma half. Okay, so here again we can also write it to be 2 pi I. So this is another convention, depending on, like, depending on what convention you are taking. So in K, if you so you can also absorb the 2 pi into the G. You can also write G as this. Or if you don't write G as this, then you can write 2 pi in front. So okay, let us change the convention a little bit. So this is the formula that we will be following. So there are both ways of doing that, but yeah, this is the formula we will be following. So there is a 2 pi factor. Okay, so these are the two things, two atomic bases. So the P is given as e to the power 0 dot h 0 dot k plus 0 dot l for 0 0 0 2 pi, and e to the power 2 pi I h dot 1 k dot 1 l dot 1. Okay, so it will be 1 plus e to the power 2 pi I h plus k plus l. Okay, so yeah, sorry, there is a half. Yeah, half. So there is a pi I to h plus k plus l. So now there is a thing to observe. If h plus k plus l is odd, then p becomes 0. If h plus k plus l is even, then p becomes 2. So that is a very interesting thing. That basically means that when h plus k plus l is odd, then the reflection will not be allowed. The reflection will not be allowed because p is becoming 0. So that is a very profound uh, kind of thing. Okay, so why is it the case? So we can actually look at the crystal and see why it is the case. So let us draw a cubic crystal. Okay, so let us say there are atoms. So this is what, this is BCC, body centered cubic, right? There is a atom which is also at the center. There is also an atom which is at the center, right? Okay. Mm, right. So what we will see is basically, I mean, in a physical sense, let's say we take 110 plane, 110 plane. So there H plus K plus L is even, right? So there will be an allowed reflection. So if you actually take that, the 110 plane looks like this. It will contain the red atoms. The red atoms will be contained. The red atoms are actually contained into the lattice. Okay. So what we can see is what will be the next plane. So the next plane will look something like this, which will contain, actually it is very hard to draw, but the next plane will contain this atom and this atom, so it will be looking something like this. Bad drawing, but okay, let me try again. Yes, so yeah, it will look something like this. So it will be parallel to the blue plane, but it will be shifted. So as you can see that the atoms are not actually on top of each other. So you can see that the reflection is not actually happening. So in this thing, let's say we said in the Bragg's condition, we assume that the D is the atoms are on top of each other, right? But here we can see the atoms are not exactly on the top of each other. If you look at the plane, so there will be a slanting D. So let's say this is the D. Now you will have this kind of a thing, right? So this slanting D will create some problems, or more, it will make the condition for constructive interference more complex. And it turns out that for BCC this will be allowed, but for example if you take a 111 plane, which will be, let's say, let me erase these things, this thing, yeah. So the 111 plane, let me draw the 111 plane by, let's say, pink. So the 111 plane, so the 111 plane does not contain, it only contains these, points. And you can actually see that if you consider these planes, you will actually sometimes you will miss points, or the points will be aligned in such a way that there will be like destructive interference, so when light falls to that plane, so we will not see any peaks from the this 111 plane. So what we will see is, let's say, go back to the our famous picture of the diffraction. What you will see is suddenly this 111 plane will disappear. So that is a very interesting thing. So we will now consider the FCC, or the face centered cubic lattice. For FCC it will be 0 0 0, half half 0, 0 half half, half comma 0 comma half. Okay, so now if you look at the P, it will become 1 plus e to the power I pi h plus k plus e to the power I pi k plus L plus e to the power I pi h plus L. So actually we can see that what are the combinations of h, k and L, which will give you some uh, non-zero p, and what are the combinations that will give you 0p. So for non-zero p, we can obviously have h plus k plus L plus h, all are even. So that is one condition that we will give you p equals to 4. Or maybe h plus k is even, k plus L is odd, h plus L is even. So that can be possible. One of them is odd. If both of them are odd, or maybe all of them are odd. So all of them even, all of them odd, but it should not be that one is even, the rest two are odd. So that should not happen. And all of them odd, that also is not possible, right? If you see mathematically, that is not possible. So the only the only situations I see is that if k plus L and L plus H are odd, so it's odd plus odd and odd plus odd. Mm, Sorry, this is even plus odd and even plus odd. Then we are not going to get anything. So yeah, I mean it's a kind of a mathematical problem. So I don't remember the exact solution, but it's pretty easy to actually calculate the exact solution. But the crucial physical concept to remember here is that, yeah, this is going to be the expression, and this p is often denoted by s. It's called the structure factor. This is called the structure factor. So, okay, so next class we are going to look at form factor, and we will formally close the chapter of crystallography, and then we will have completed a crystallography, and how in every experimental situation you will see that the g vectors or the reciprocal vectors are coming. And after motivating that, we are actually going to delve into theoretical models about electrons and how they use reciprocal lattice vectors and how they build upon them. So see you in the next class. Best of luck.